We all know that water is essential for the survival of all forms of life. It forms a major part of all living organisms. 60% of the human body is made up of water. And in some plants, this quantum goes up to 90%. Water covers 71% of the Earth's surface. However, the distribution of water over the Earth's surface is not uniform. Oceans contain 97.33% of water on the Earth's surface. Only 2% of water on the Earth's surface is in the form of polar ice and glaciers. The remaining water, less than 1%, is present in lakes, rivers, in the atmosphere, and as underground water. Let us now look at some physical properties of water. Water is a tasteless and odorless liquid at standard temperature and pressure. It freezes into ice at 273 Kelvin. Its boiling point is 373 Kelvin and has a density of 1 gram per cubic centimeter at 298 Kelvin. Water has strong hydrogen bonding in its molecules and, therefore, exists as associated molecules. Due to the presence of extensive hydrogen bonding in its molecules, water has a high freezing point, a high boiling point, a high heat of vaporization, and a high heat of fusion in comparison to hydrides formed from other group 16 elements, like H2S and H2SE. In comparison to other liquids, water has high thermal conductivity, surface tension, dipole moment, and dielectric constant respectively. And also, it has highest specific heat. These properties allow water to play a key role in the biosphere. Its high heat of vaporization and high heat capacities are responsible for the moderation of the climate and the body temperature of all living beings. Water is an excellent solvent for the transportation of ions and molecules required for animal metabolism. Due to hydrogen bonding with polar molecules, even covalent compounds such as alcohol, and carbohydrates dissolve in water. The shape of water molecule is bent or V-shape with a bond angle of 104.5 degrees and OH bond length of 95.7 picometers. In water molecule, as the oxygen atom has a higher electronegativity than hydrogen atom, it carries a partial negative charge, whereas the hydrogen atom carries slightly positive charge. As a result, water is a polar covalent molecule. In the liquid phase, water molecules are associated by hydrogen bonds. The crystalline form of water is ice. At normal atmospheric pressure, ice crystallizes in hexagonal form. The density of ice is 0.9167 gram per centimeter cube at 273 Kelvin, whereas water has a density of 0.9998 gram per centimeter cube at the same temperature. In winter, The frozen ice on surface of the lakes provides thermal insulation and is important for the survival of aquatic life. Ice has highly ordered three-dimensional hydrogen-bonded structure, in which every oxygen atom is surrounded tetrahedrally by 4 other oxygen atoms at a distance of 276 picometers. Hydrogen bonding gives ice a rather open crystal lattice structure with wide spaces between the molecules. These vacant spaces can hold some other molecules of appropriate size interstitially. Chemically, water reacts with large number of substances. Let us look at some of these reactions. Amphoteric nature. Water is amphoteric in nature, which means that it can act as an acid as well as a base. According to the Lowry-Bronsted concept, water can act as an acid by losing a proton and as a base by accepting a proton. For example, in the reaction with ammonia, water acts as an acid by giving H+ ion and forming NH4+ ion. In the reactions with hydrogen chloride and hydrogen sulfide, water behaves as a base by accepting H+ ions and forming H3O+ ions. Water also undergoes autoprotolysis or self-ionization, in which one molecule of water acts as acid 1 and another molecule as base 2 to give a molecule of acid 2 and base 1. These are also known as conjugate acid and conjugate base. Redox reactions involving water. Water can easily be reduced into hydrogen by highly electropositive metals. For example, sodium metal reacts with water to give sodium hydroxide and hydrogen. Therefore, it is a great source of hydrogen. Water is oxidized to oxygen during photosynthesis. The reaction that takes place is 6 molecules of carbon dioxide react with 12 molecules of water to give 1 molecule of glucose, 6 molecules of water and 6 molecules of oxygen. It also reacts with fluorine gas to give oxygen and ozone. Hydrolysis reactions. Water is a strong solvent and dissolves many ionic compounds. However, due to its high dielectric constant, it has very strong hydrating tendency and can easily hydrolyze many ionic and covalent compounds. Water hydrolyzes the oxides and halides of nonmetals to their respective acids. For example, it hydrolyzes phosphorus pentoxide to give orthophosphoric acid. It also hydrolyzes silicon tetrachloride to hydrochloric acid and silicon dioxide. Water also hydrolyzes the carbides, hydrides and nitrides of some metals. For example, it hydrolyzes both calcium carbide and aluminium nitride to give ethine and ammonia respectively. The reactions that takes place are: calcium carbide reacts with water to give calcium hydroxide and ethine. Water reacts with aluminium nitride to give aluminium hydroxide and ammonia. Hydrate formation. Many salts can be crystallized as hydrated salts from their aqueous solutions. There are three types of hydrates. The first type of hydrate is coordinated water. For example, in CrH2O6 3 plus 3Cl minus, water molecules are coordinated to metal ions in a complex. The second type of hydrates is interstitial water. For example, in BaCl2 2H2O, water molecules occupy interstitial sites in the crystal lattice. In the third type of hydrates, water molecules are hydrogen bonded to certain oxygen-containing anions. For example, in CuSO4 5H2O, one water molecule is hydrogen bonded to sulfate ion, and the other four molecules are coordinated to give CuH2O4 2- plus SO4 2H2O. Water is classified as soft and hard depending on the type of dissolved salts and behavior with soap. Soft water produces lather easily with soap and contains no calcium or magnesium ions. A good example of soft water is rainwater. Hard water, on the other hand, does not produce lather with soap easily and cannot be used for laundry. For example, river, sea, and sometimes even well water. The hardness of water is due to the dissolved salts, like bicarbonates, chlorides and sulfates of calcium and magnesium ions. When rainwater makes its way through the ground, it dissolves the salts of calcium and magnesium and turns hard. Let's see why hard water cannot be used for laundry. Hard water contains calcium and magnesium cations, which react with soap to form scum or precipitate of calcium and magnesium salts or fatty acids. Laundry soap contains sodium stearate. When sodium stearate reacts with the calcium and magnesium salts, it forms calcium and magnesium stearate precipitate. Until all the calcium and magnesium ions are precipitated, lather is not produced. This is why hard water is unsuitable for laundry. Hard water is also harmful for the boilers because of the deposition of salts in the form of scales, which reduces the working efficiency of the boilers. Hardness of water can be classified as temporary hardness and permanent hardness. Temporary hardness of water is due to the presence of soluble calcium and magnesium hydrogen carbonates, respectively. There are two common methods to remove temporary hardness. The first method is boiling. Hard water is taken in a large boiler. During boiling, the soluble magnesium hydrogen carbonate is converted into insoluble magnesium carbonate, while calcium hydrogen carbonate changes to insoluble calcium carbonate. The precipitates of magnesium carbonate and calcium carbonate are removed by filtration, leaving soft water as the filtrate. The second method to remove temporary hardness is known as Clark's method. In this method, a calculated amount of lime is added to hard water. It precipitates out calcium carbonate and magnesium hydroxide, which can be filtered off. Permanent hardness is due to the presence of salts of magnesium and calcium in the form of chlorides and sulfates. Permanent hardness cannot be removed by boiling. It is removed by other methods, which include treatment with washing soda, Kalgin's method, ion exchange method, synthetic resins method. Let us look at each of these methods in detail. Treatment with washing soda or sodium carbonate. A calculated amount of washing soda is added to hard water. Washing soda reacts with the soluble chlorides and sulfates of calcium and magnesium in hard water to form insoluble carbonates. The second method of removing permanent hardness is Kalgin's method. In this method, calcium and magnesium ions are not removed from the water, but are rendered ineffective by the addition of sodium hexametaphosphate, commercially called Kalgin. Calcium and magnesium ions react with Kalgin to form a soluble complex. The complex anion keeps the magnesium and calcium ions in solution, not allowing them to react with soap. In ion exchange method, also called the zeolite or permutate process, hydrated sodium aluminium silicate or zeolite, when added to hard water, exchanges cations such as magnesium and calcium ions for sodium ions. For simplicity, sodium aluminium silicate NaAlSiO4 is written as NaZ. Once all the sodium in the zeolite is used up, it is regenerated for further use by treating with an aqueous sodium chloride solution. The fourth method of removing permanent hardness is the synthetic resins method. In this method, synthetic cation exchanges are used. This method is more efficient than the zeolite method. Cation exchange resins contain larger organic molecules with groups such as SO3H or COOH that are water insoluble. They exchange their H+ ions with the cations in hard water. Anion exchange resins contain organic molecules with groups such as NH3OH that exchange their OH- ions with the anions present in hard water. Pure demineralized or deionized water, free from all soluble mineral salts, is obtained by passing hard water successively through a cation exchange in the H+ form and an anion exchange resin in the OH- form. In the cation exchange process, the H+ ions in RCOO-H+ are exchanged with sodium, calcium and magnesium ions present in the hard water. The reaction that takes place is RCOOH in solid state plus M2+ in aqueous solution gives MrCOO taken twice plus 2H+ ions in aqueous solution, where M+2 is a calcium or magnesium cation. Since this reaction releases H+ ions, it makes water acidic. In the anion exchange process, RnH2 in water gives RnH3 plus OH-. The OH- ion in RnH3 plus OH minus gets exchanged with chloride, bicarbonate and sulfate anions present in the water. The reaction that takes place in RnH3 plus OH minus reacts with X minus to give RnH3 plus X minus and OH minus ions, if X is chloride ion. The released OH minus ions neutralize H plus ions. Once the cation and anion exchange resin beds are exhausted, they are regenerated by treatment with dilute acid and alkali solutions respectively. Hydrogen peroxide is a very pale blue liquid and appears colorless in a dilute solution. It is naturally produced in organisms as a byproduct of oxygen metabolism. It is a strong oxidizing agent. In fact, it is such a highly reactive oxygen species that all living aerobes form peroxide enzymes to decompose the hydrogen peroxide formed within the body into water and oxygen harmlessly and catalytically. Structurally, the hydrogen peroxide molecule is non-planar. It has an open book structure. The presence of lone pairs of electrons on the oxygen atoms and the hydrogen bonding gives the molecule a different structure in gaseous and solid phases. In gaseous state, hydrogen peroxide has a dihedral angle of 111.5 degrees, whereas in solid state, at a temperature of 110 Kelvin, it has a dihedral angle of 90.2 degrees. This affects its physical properties. It has a melting point of 272.4 Kelvin, a boiling point of 432 Kelvin, a vapor pressure of 1.9 millimeters Hg, a solid density of 1.64 gram per cubic centimeter, and a liquid density of 1.44 gram per cubic centimeter. Its viscosity is slightly higher than water at 1.25 centipoise. Its dielectric constant at 298 Kelvin is 70.7 Coulomb square per Newton meter square. And electrical conductivity is 5.1 into 10 raised to minus 8 ohm per centimeter. Chemically, it acts as an oxidizing as well as a reducing agent in both acidic and basic media. So, let's now look at the reactions that take place in acidic media. In an acidic medium, as an oxidizing agent, hydrogen peroxide reacts with ferrous ions to form ferric ions. As a reducing agent, it reacts with sodium hypochlorite and yields water, sodium chloride, salt, and oxygen. This reaction is also used in laboratories to prepare oxygen. Now, let's look at the reactions that take place in basic media. Here, as an oxidizing agent, hydrogen peroxide reacts with ferrous ions to form ferric ions. As a reducing agent, it reacts with iodine to form iodide ions along with water and oxygen. For example, if potassium hydroxide is taken as the base, then potassium iodide salt is formed. On exposure to light, hydrogen peroxide undergoes slow decomposition to form water and oxygen. Metals and traces of alkaline compounds hasten this reaction. And this is why hydrogen peroxide is always stored in plastic bottles and kept in the dark. In recent years, the demand for hydrogen peroxide has increased as it has found widespread use in pollution control treatment of domestic and commercial effluents. In laboratories, hydrogen peroxide is prepared from barium peroxide or acidified sulfate solution. To obtain hydrogen peroxide from barium peroxide, first acidify barium peroxide with sulfuric acid. Barium sulfate is precipitated and an aqueous solution of hydrogen peroxide is produced. The excess water is then removed by evaporating the solution under reduced pressure. This will give us hydrogen peroxide. You can also obtain hydrogen peroxide from 50% sulfuric acid solution. The solution subjected to electrolytic oxidation to yield peroxydisulfuric acid. The peroxydisulfuric acid formed undergoes hydrolysis to form hydrogen peroxide. During electrolysis, hydrogen peroxide is formed at the anode. Peroxydisulfuric acid is formed as a byproduct at the anode. Hydrogen gas is evolved at the cathode. Commercially, hydrogen peroxide is prepared by auto-oxidation of 2-ethyl anthraquinol. First, air is passed through 2-ethyl anthraquinol to yield 2-ethyl anthraquinone and hydrogen peroxide. The product, 2-ethyl anthraquinone, is then reduced. For this, hydrogen under a pressure of 1 to 3 atmospheres at 4 degrees centigrade is passed over 2-ethyl anthraquinone. This gives back 2-ethyl anthraquinol, the reactant. This reaction gives a dilute solution of hydrogen peroxide. It is then extracted with water and the solution of the required concentration is prepared. It is customary to indicate the strength of hydrogen peroxide solution in terms of the volume of oxygen at NTP that 1 volume of hydrogen peroxide gives on heating. When the grade of H2O2 in volumes is given, its percentage strength can be calculated. We come across many uses of hydrogen peroxide every day. For example, as a mild disinfectant, as a cleanser, as a bleaching agent in the textile, paper pulp, leather, oils and fats industries, as a pollution control agent in the treatment of domestic and industrial effluents, oxidation of cyanides, restoration of aerobic conditions to sewage wastes, and so on. Thus, we see that hydrogen peroxide is an important compound. Today, we mostly use fossil fuel to power our growth. The demand for fuel is so huge that it is believed that by the middle of the 21st century, the world will run out of fossil fuel. For this reason, the race is on to develop alternative energy sources. One of the major alternative sources in use today is nuclear energy. However, it can only be used to obtain electrical energy, but only 20% of the total energy required constitutes electrical energy. So, For the remaining 80% energy requirement, scientists are still searching for a viable energy source. One of the most promising alternatives they are currently studying is the use of hydrogen as a fuel. Hydrogen has many advantages over all other options. For example, it is abundantly available. Its combustion product being water, it is pollution-free. It yields almost double the energy provided by jet fuels. For example, liquid hydrogen is used as a rocket fuel. This fuel has water as its product instead of harmful carbon dioxide, sulfur dioxide, and other hydrocarbons. However, it is not yet used on a large-scale basis because pure hydrogen gas is not readily available. Hydrogen gas is highly flammable and explosive to handle. Storage and transport of hydrogen gas is very expensive. The cost of production of hydrogen is very high at this point of time. Although some cars using hydrogen fuel are already in the American and European markets, commercial use of hydrogen as one of the most eco-friendly energy alternatives has still a long way to go.